Hi, I'm Lauren Fontenot, and today I'll be discussing the effects of unilateral real-time biofeedback on propulsive forces during gait. So this experiment was conducted to test able-bodied individuals' ability to unilaterally manipulate push-off forces in the targeted limb by using real-time auditory and visual feedback. The push-off forces were measured using AGRF. The main results from this study found that compared to the pre-training trials, an increased AGRF in the dominant leg was recorded. Increased AGRF was also retained after short breaks, proving that this skill can be recalled through short-term memory. This was achieved by providing real-time biofeedback cues, which allowed for self-correction of gait pattern while the subject was being tested. So the research problem. The problem being addressed in this study deals with hemiparesis in post-stroke patients. Many individuals experience reduced push-off force in the paretic leg throughout terminal stance phase. This in turn leads to negative effects on gait speed, inner limb symmetry, and overall walking function. By conducting this study, researchers hope to find ways to improve rehabilitation treatments for non-able-bodied individuals. The research hypothesis. Researchers hypothesized that a single session of unilateral AGRF biofeedback would produce an increase in the targeted limb without affecting AGRF in the contralateral limb. Visual and auditory feedback was studied on its ability to elicit AGRF increases during real-time testing. I agree with the logic of the study. Biofeedback also allows for self-correction, self-awareness. Once the self-awareness is made, individuals are more aware of the necessary adjustments to be made to achieve the targeted AGRF. So the method. 7 able-bodied individuals participated in this study. All participants were right leg dominant, and participants were excluded from the study if they possessed any factors affecting their gait. The study consisted of 11 minutes of continuous walking at a self-selected speed on a dual belt treadmill. Walking speed was independently chosen by each participant. During pre-training, which consisted of the first 30 seconds of the study, normal gait was assessed and a baseline value was recorded. The initial walking trial was used to calculate average peak of the AGRF by the dominant leg for 10 gait cycles. During training, auditory and visual feedback was provided using a display screen and speaker. The visual feedback consisted of a horizontal line graph that showed anterior and posterior GRF of the targeted leg. A targeted AGRF range was calculated, this being 20 to 30% increase from the participant's initial peak AGRF. When the participants reached the targeted AGRF, an audible beep was given. Biofeedback was provided for the rest of the 10-minute and 30-second duration of the first 11-minute trial. Phased feedback dosing of the visual and auditory cues was used. Visual and auditory feedback was given during 4 2-minute periods, followed by an absence of feedback. The periods without feedback lasted 15 seconds, followed by the increments being increased by 15 more seconds each period. 2 30-second post-training trials were collected without the use of biofeedback, and differences in peak AGRF were compared for pre- and post-training. After the 11-minute training, individuals took a 2-minute standing break before beginning a retention test. After the 2 minutes, individuals began walking at their normal gait for 30 seconds. They were then instructed to try and repeat the walking pattern they were doing earlier. This was to test whether individuals are able to switch between gait patterns on command. After another 2-minute standing period, the retention test was repeated again, the same as previously conducted. No biofeedback was given during each retention test. And on the graph right here, you can see where the auditory feedback was given, and this is the visual biofeedback. The dependent variable of this study was the peak AGRF from the right leg. GRF values of the gait cycle was studied before, during, and after training. GRF values during the retention test also served as a variable to help determine whether or not peak AGRF reached the targeted value. The secondary values measured were timing of peak AGRF, vertical GRF, cadence, and temporal parameters. Temporal parameters include stance, stride, and swing duration. The results. Representative data showed to have increases in targeted leg AGRF production during propulsive phase of the gait cycle during biofeedback when compared to pre-training. There was no significant differences in the timing of peak AGRF during pre- and post-testing. Vertical GRF showed that the left peak was significantly greater at post-testing compared to pre-training. The right leg showed a reduction of cadence during post-test when compared to pre-training. Cadence for the left leg was significantly smaller during post-test. Right and left leg stance duration showed a significant increase during post-test. The graph on the left demonstrates the standing error for the dominant legs before, during, and after training. Standing breaks are shown by the vertical lines. The star represents a significant greater peak AGRF compared to peak training. The graph on the right demonstrates the coefficients of variation for the peak AGRF generated by the dominant leg, pre-represented by the solid bars, and the non-dominant leg represented by the striped bars during multiple time periods. Overall, the participants showed increase in peak AGRF production in the targeted leg after 11 minutes of biofeedback training. These results were found within the first minute of training and maintained throughout the rest of the biofeedback intervention. Increased peak AGRF was also presented in the absence of biofeedback during the retention test. Increases in stance duration and decreases in cadence in the targeted limb were seen after biofeedback training. There were no AGRF increases in the non-targeted leg, the left leg. This suggests that unilateral biofeedback was successful in only increasing peak AGRF values in the targeted leg. Individuals were also able to switch between normal and modified gait patterns upon command. This suggests short-term memory retention of the modified gait. Able-bodied participants can rapidly change their motor control in order to increase AGRF production. So I agree with the author's interpretation of the results. The study provided the effect of real-time gait biofeedback. Sorry, let's just start that over. So I agree with the author's interpretation of the results. The study proved the effect of real-time gait biofeedback had an increasing targeted AGRF unilaterally without interfering with the non-dominant leg. There was a clear difference in data when comparing pre-training, post-training, and during training. This study lacked kinetic data of the ankle, knee, and hip. More data on these kinetic aspects would further explain the increased peak in AGRF. This can also give information of how some external factors can skew results. For future studies, one could think of including non-able-bodied participants, for instance, post-stroke hemiparesis participants that we discussed at the beginning of this presentation. And that is the end of my presentation. Thank you for watching.